Okay, at this time, I would welcome questions from in-person students and online students. Okay, yes.
So if we already chose the robot arm, but you just discussed about doing, if we want to be more software oriented, doing the courses, did you mention that they were all paid for, or some of them free?
Some of them are free.
Okay, and that would take place of that
That
problem.
would be in place of the robot arm
Okay.
because it's totally up to you. If you look at, there are about 10, 15 projects. If you look at the combination,
It's in Canvas?
Yeah, in Canvas.
Okay, okay.
Everything is in Canvas. Yes.
So you had mentioned can it be 3 people or the maximum?
Okay.
Good. All right.
3 is a crowd.
Okay.
Yes.
Okay, so I think I have two questions. One is, if we choose to do one of the online courses, do you think that that would make it more difficult for us to do the other in-class homeworks because it's not really aligned, what we're learning doesn't align as well with what you're teaching, or does that not matter as much?
Let me finish 1 or 2 classes,
Okay,
and then you realize that I teach a totally different fashion. So I don't see any problem in doing any of the homework or quizzes. So as long as you come to class, attend the class, you should be fine.
okay.
But just to address the other question, but if you think about it, the time is limited. I cannot teach you all the things I would like to teach, and your interest may be a little bit different because we have students from artificial intelligence background, we have students from electrical engineering background, we have students from biomechanical engineering background, and we have students from system engineering background. So I want you to kind of pick and choose the skill set that you want to develop. Yes.
Okay, so also if we choose project 2, do we have to also tell you exactly which course we're doing now?
Yes.
No? Okay.
Yes, because there is a reason for this. There are some free courses that you can enroll and that you can start immediately. But there are some paid courses which they start today. So basically, if you decide to go paid route, and trust me, I'm not gonna get any money or commission from those classes, but my students have done those courses and they think they are very good when they go in the job market because they talk about machine learning, deep learning. There is an excellent course on TensorFlow if you want to become a machine learning engineer. TensorFlow, TensorFlow or Terra, those are the important frameworks that you should know. And unfortunately, at ASU, nobody teaches those classes. So, for example, ROS is super important, but there is not a single course where it's just like ROS. If you take a course in perception or some other area, they will use ROS to do the project. So if you want to take the ROS class, it will be very helpful if you go and take the perception class or machine learning class in your second or third semester.
Okay, sorry, one other question. If we are there and we want to do an honors project, is it possible to do that while doing the second project, or would we have to do the first project?
I would always recommend for students not to be adventurous. The reason for that is I want you to be successful. So for Barrett students, if you want to do a project, I would strongly recommend working individually. So if you are the Barrett student, actually select the project 1, but say I'm gonna work alone, and I would give you Barrett credit for that. If you are a Barrett student, but say I am interested in one of those software projects, those are individual, so you have no other choice but to work on your own. But that's a lot of fun. Yeah.
So if I choose project 1 and I got stuck somewhere with the complexities or something like that, so what are the resources available for me to resolve those things and get it going?
Without you getting stuck at what point, I don't know what resources can be made available to you. But trust me, that project is super simple. It's like recipe, step by step. And why I know this? Because I ran that project multiple times in a class of 60 students and everyone did it. So I don't anticipate you getting stuck. The only issue that you may find it is difficult is the innovation part, wherein I ask you to either interface that with the webcam, but then you can select a very simple case, like just tuning the robot so that the motion is smooth. That is mostly trial and error. Or asking robot to draw an alphabet. The easiest alphabet to draw is I. Or ask robot to draw a circle or a triangle. But no point. So it's not, you just go through it. Once you come to that point, I can suggest to you that okay, this is it actually they are very super easy. I don't worry about it.
Do we have to specify what our extra part is in project one now, or do we just say we're doing?
No, you do the project one and finally once how comfortable you
Later.
feel with the robot. Because I tell you, to build a good robot, you need skill and will. Because as you can see, this is not one of the best robots that my students built. But if you Google, you will see the videos of the robots students built. This is little wobbly. And that is because of the clearances. So if you want to build a very nice, beautiful robot, you will have to make sure the tolerances are correct. Each joint is properly assembled. The joint, if you see here, and I will let you take a look at the robot and play with it, there is backslash. So there is no backlash and all that stuff that you need to take care. So it's a skill. Yeah.
So, first class, I didn't really comprehend our second choice, and I had already chosen the robotic arm. Is there any possibility that I can switch it so that I can take the 3 course?
As long as you can change your choices by tonight.
It says only one attempt. Only only one attempt.
Okay, only one attempt. I will make an exception.
Thank you.
So just what course would you recommend to take in that free courses? What do you think will be more useful for you? It depends on where you want to go, master. If you want to go work for Facebook or Google, I would recommend take the nano degree program in robotics software. It basically is a comprehensive course and get the certificate, put it on your LinkedIn, and that will be an additional feather in your hand. But if you want to go work, if you want to go work for some automation, so it totally depends upon your background. And if you want to log in to university, they will give you the curriculum. There will be graduates. You can actually go onto the LinkedIn and see how many of students who are working in, or how many of engineers working in the organization that you want to work, they have done these classes. Many of my students have done those classes, and I can guarantee you that they tell me that it was very helpful when they went to industry. A question?
You have questions on the.
Oh, wow. Thank you. Okay, now I am going to answer the question from online students. Can online attendees have a picture or video of robot being displayed in person? Yeah, somebody's phone is ringing. Yes. So here is what I'm going to do. Now you should be seeing me. Can you see me, online students? Okay, now you see the robot. I think I should switch the video. Okay. Now you should see the robot. Can you see the robot? And if you are wondering what is at the bottom, those are omnidirection wheels. So basically, the ground vehicle can go left, right, front, back in the position that it is. If you want to see the bigger version of this, we have built that and I have that in my lab. This is a small version. So actually 15 feet version I have in the lab. So, and actually it is actually much nicer. It's on the Caesar jack and it's actually on the Caesar mechanism. Okay, anything else you want to see?
I think there was a question before that one.
Oh, there was a question before. Okay. Okay, this is it. Okay, there was a question. Wow, lot of yeses. Yeses. That would be robot. Would the components row? Yes. To answer Muskan's question, high cost items. No, I won't give you webcam because it won't be, it will be unique to your project. But I will give you the projects like servos and other stuff. But the small components like uh, um, the screws, or if you want to make the robot super nice, you would have to add some sleeves, some bearings that you will be responsible for. But I don't think they're expensive. I will give you servos, I will give you an Arduino, I'll give you a power supply. So the high cost items will be given to you, but you will be responsible for buying the fasteners, and that's up to you. Because if you select wrong type of fasteners, this is what happens. So that is up to you. Then you have to select washers. So it's totally up to you how you want to do it. But the basic material will be given to you, and you will just get one set. If you try it, you will be responsible for purchasing the required components. Yes.
So you said that you could scale up the project to different sizes. So the servers that you will be giving, will they be the same, or you could have a?
I wouldn't say don't scale the project now because you will need monster servos.
Right.
And then you can't 3D print. I mean, we have a commercial industrial 3D printer which can build actually 3D print about 3 feet of structure. But for this class, we will stick to this size. We don't want anyone to get hurt, and it's not easy to work with industrial robots. Yeah.
Is there a deadline for picking a partner? Like that you have to like.
You need to decide by today.
Okay.
Today, 11:59 p.m. So if you are selecting project 1 with a partner, in your text box, write the project 1, and in the parentheses, write the name of your partner. Okay. Yeah.
Okay, so I submitted yesterday an old project. Could you open it back up?
You can.
So I can put the part.
Yeah, oh, don't worry about it. Then you can just the partner that you have you selected a partner or no? So ask your partner to put your name.
Can I favor submit it?
Yeah, no, don't have to resubmit it. The only reason is I want to have teams, because then I'm gonna give it to Borna, and then we can distribute the part.
I don't want to say is we both submitted it and we didn't put each other's names.
Okay, so you want me to, or you can send me an email and I'll make that correct. Lot of time. Any other questions?
So, what is the cost for 3D printing?
I think you have to purchase the material, and if you buy material from Amazon in bulk, it's super cheap. It's not expensive at all. Does anyone know about the new innovation hub policies on 3D printing?
Can't you just go up to the computer and then put answer in his class?
That may be the case. So I don't know how they set it up because the process keeps on changing.
Also, I know that the additive manufacturing class is in there right now on most of the printers. If most of us are trying to print a robot as well, how is that going to line up?
Oh, a wee bird gets the worm. So basically, here is what I would recommend. There are excellent 3D printers that you can buy for $60. And I can make some recommendations. So because in my last class, 4 students came together. Everyone just pitched in $15, and they bought a 3D printer, and that printer paid off. And then one of the students bought it. So he actually gave everyone $5 back. Like that. I can send you the recommendation, but I will have to go back and look at the eBay because if you want, I can send some recommendation of 3D printers. And I would, if you are interested in playing with all this stuff, perhaps taking my robotics 2 class, a 3D printer is not a bad investment at all. If you have 4 students, 2 teams working together, you can buy a very nice small footprint 3D printer for $70-80. If you want to go large, you can get it about $100-120. Yeah.
I think there is a workshop near the Engineering Research Center in Delhi campus, which if you tell if it's a college project, they give the printing for free.
I don't know because those policies keep on changing. So it's totally up to you. I mean, I'm sure there are lots and lots of resources. Okay, any other questions? Okay. I don't see any questions. So I'm gonna start today's lesson. And as I told you, I'm gonna teach this class in a slightly different fashion. So here is what we are gonna do. Yeah.
For the assignment one, like I started it on Thursday and I couldn't finish it till now. I do it 5 hours per day, but I couldn't finish it till now. It's taking a lot of time.
I know. So here is the sad truth about life. Initially, things are difficult.
It's too easy, but it's exhausting.
But gradually you get used to it. Okay. All right. So what I'm going to do is I'm going to suggest, I don't know, have you seen the course Learning How to Learn? There is a course that teaches you learning how to learn. And apparently it's very famous class. So, and it's available for free. Okay, so you can check it out. So what I'm going to do is, I'm going to suggest you a very simple learning technique. Okay, and my hope is that it will resonate with some of you, and that way you will be able to grasp a lot of information and a very short period of time. So I would encourage you to try it out. So in this technique, what I'm going to do is I'm going to teach each concept 2 times faithfully. I'm going to teach each concept 2 times. First time when I'm teaching it, here is my recommendation. Close laptops, close everything, close phones, and just pay attention on the board, or just see or try to tune in with the material that is delivered. So close everything, just full attention on what I'm saying. Even don't lift your pen, don't move down anything. Then once I'm done with explaining the concept for the first time, then what I'm going to do is I'm going to go back and repeat what I said. And at that time, you should note down and take the note. And I have found this type of learning very efficient. That way, I think the out-of-class learning for students is minimized, because most of the understanding of concept happens in the class. So I would encourage you to try it and let me know if it works, because I have been receiving a lot of good feedback on this technique. So first time, when I'm going to discuss some concepts, I would encourage you to close. I mean, I'm not going to check, but I would encourage you to close your laptops, turn off your phones, just look at the screen, and at that time, ask every question. So if you have any question you don't understand, nothing wrong. So just ask away and ask me questions like, how did you get this? How did you get that? And then what I would do is I will say, okay, this is the time you can copy down. So you are welcome to take down the notes when I'm explaining the same concept for the second time. Everyone understood? If you don't want to note down anything, that's totally cool, because these notes are going to be available on Canvas anyway. Are we good? Okay. Enjoy the ride. So in today's class, what I'm going to do is I'm going to talk about forward kinematics. Now, what do I mean by forward kinematics? Forward kinematics is given the joint angles and positions, find position and orientation of end effector, typically denoted as EE. So for an example, if you have a very simple robot, what I would do is, if I want to solve the forward kinematics problem, I can give the joint angles. So I can give this angle as theta. I can give this angle at theta 2, theta 1. And if this is an end effector, think about it like a pen. Okay. So given the values theta 1 and theta 2, I want to find out 6 things. I want to find out X, Y, and Z location of the end effector, and 3 orientations. And orientations could be defined in multiple ways. I'm going to say, just for the sake of simplicity, rotation about X. So rotation about X, Y, and Z. Now this problem looks simple in a sense that if I provide theta 1 and theta 2, if the link lengths L1 and L2 are fixed, then from the geometry, I should be able to find out the values of the end effector position and end effector orientation. Now the tricky question is, how do I solve forward kinematics problem in 3 dimensions? So forward kinematics problem in 2 dimensions is super simple, because what you can actually do is you can take a graph paper, you can draw the robot, and then based on the length and angles, you can find out what is the position and orientation of the robot. Now, the forward kinematics problem is tricky and difficult in 3 dimensions, because now you could have not only have multiple reference frames, but those reference frames could be oriented in different orientations. So how do we solve this? And solving a forward kinematics problem in 3 dimensions is just similar to how do you eat an elephant in pieces. So what we do is we assign coordinate systems, we find the relationship, and then we derive something called as the rotation matrices and homogeneous transformations. And now I'm going to show you a totally different way of looking at homogeneous transformations. Unfortunately, this approach is not given in the textbooks, at least the textbooks I know. So please pay attention. So forward kinematics problem is finding the end effector position and orientation given the joint angles and positions. There are 2 types of joints in robots. One is a rotary joint, and the second one is a prismatic joint. Rotary joint is nothing but sort of a hinge, and prismatic joint is sort of a cylinder. And the idea is, whenever you see a super complex robot just like this, first and foremost, we should be able to identify the rotary joints and their locations. So let's do this thought exercise. So if you see the robot that I showed the picture of, there is one rotary joint here, one rotary joint here, there is another rotary joint here, there is one rotary joint here, and there is a joint for the gripper. But here is the problem, that
if you visualize the way these rotary joints are, they are oriented in space. They are not in a plane. So what we need to do is, whenever we look at a robot, small robot, big robot, parallel robot, series robot, doesn't matter. We should look at that as some sort of mechanism with different links and different joints. We absolutely need to do that to construct something called as kinematic diagram. So kinematic diagram is going to be the key when we try to solve a robot. So rotary joints, I'm going to represent like this in a kinematic diagram, and prismatic joint, I'm going to represent like this in the kinematic diagram. So this is the axis where the rotary joint is actuated. This is the axis where prismatic joint is actuated. Everyone understood? So next part, I'm going to talk about rotation matrices. So first part is, remember this, when you see a robot, you need to sort of fragment a robot into links and joints. There are two types of joints, rotary joint and prismatic joint. So at the end, we want something similar to the free body diagram. You want to construct the robot, a bare bone robot, a geometric representation of the robot that only constitutes links and joints. Any questions? No questions? Very good. Now what I want to do is, and next part, what I'm going to discuss is super duper important. So everyone pay attention. What I want to do is, imagine a case wherein I have a three-dimensional coordinate frame. And this part is super duper important. So everyone, please pay close attention, because I'm going to teach this one more time. But once you master this, the robotics, forward kinematics, inverse kinematics, dynamics would be super duper simple. So I have these three coordinates. This is my X, this is my Y, this is my Z. In the last class, I talked about the positive rotations. When a rotation is positive, curl your finger in the direction of rotation. If your thumb is pointing towards the axis, that rotation is positive. So what I'm going to do is, I'm going to rotate this axis about Z axis by amount. Say I'm going to call this theta, or I can call it theta Z. So check this out. What I'm going to do is, initially my axes are X, Y, and Z, or I'm going to call that X naught, Y naught, and Z naught. My Z1 coincides with Z. So my Z1, I'm going to use a different color. My Z1 coincides with Z, but I'm going to rotate by amount, say theta Z. And this rotation is positive. Curl your finger, right hand, curl your right hand fingers in the direction of rotation. Thumb is pointing towards positive Z. So rotation is positive. What does this rotation do? This rotation will rotate the X axis and the Y axis. So when these axes get rotated, I'm going to show you these rotated axes. So this is going to be my X1. This is going to be my Y1. And this angle is going to be theta Z. This angle is going to be theta Z. Everyone understood? How many of you have studied? Yeah.
So theta Z is always going to be equal to the amount that it rotates on that specific axis.
In this particular case. So what I'm saying is, initially everything was good. X0, Y0, Z0 was my axis. I applied the rotation theta z about z0 and z1 axis because those two axes are aligned, and my frame got rotated from x0 to x1 and y0 to y1. Have you studied rotation matrices before? Anyone? Okay. Prepared to be amazed. The stuff that is coming next is legendary. So what I'm going to do is this. I am going to draw, and you may say, oh, this is something that we do all the time, but I'm going to draw vertical lines. In other words, I'm going to construct two triangles. Yes. Oh, raise your hand online. Yeah, I don't see who. Okay, participants, somebody raised a hand. I don't see anyone raising a hand. Okay, it was a mistake. No worries. Okay, no worries, no worries, no worries. So what I'm going to do is this. I'm going to find out the rotation matrix. And this is the one of the most important rotation matrix that you will see. So here is how you find a rotation matrix. I have two sets of axes. I have two sets of axes. And what I'm going to say here is, so projection of, and I'm going to say here projection on. And I would emphasize this. I cannot emphasize this less because this is not discussed in any of the books. So what are my new axes? So what are my new axes? My new axes are x1, y1, z1. What are my old axes? My old axes are x0, y0, z0. Simple, right? I have new axis on top, old axis vertical. Now here is what I'm going to do. Look at x1. Projection of x1 on x0, assuming it's a unit vector, is cosine theta z. You agree with me? Now, what I want you to do is, so I'm going to say projection of x1 on x0 is cosine theta z. Now, clearly, this vector is in the same direction as x0. So that's why this has a positive sign. I didn't say that, but this is positive. Now, projection of x1 on y0, and I want you to look at this closely. Projection of x1 on y0 is sine theta z. Again, that is positive. Projection of x1 on z0 is, okay. Now next stuff. I'll start with the easy part first. So z1, projection of z1 on x0. z1 on x0 is 0. Do you agree with me? z1 on y0 is 0. Agree with me? z1 on z0, 1. Now projection of y1 onto x0. Projection of y1 onto x0, and wow, so you already know. So this is going to be sine theta z in the negative direction. So minus sine theta z. And why it is negative? Because if you look at the vector, this projection is opposite to x0. x0 is going towards right, the projection is going towards left. y1 on y0. So y1 on y0 is cosine theta z. And y0, y1 on Z naught is 0. Do you agree with me? This is how you construct the projection matrix. Now, once you master this concept, the idea would be super simple. So I'm gonna repeat this one more time, and you're welcome to copy down if you want to. So what we are gonna do is we have two axes. We have x0, y0, and z0. If you look at the way the rotation matrices are defined in classic kinematics textbooks or robotics textbook, they will show you the projection of the vectors and they will resolve. But I would strongly recommend you to use this graphical approach where you notice that projection of the new coordinate frame will be here. So your columns would be the projection of new coordinate frame. The rows are going to be the projection of old coordinate frame. So, and what I'm going to do is I'm going to use the rotation matrix to find the projection of the new coordinate frame, which is x1, y1, z1 onto x0, y0, z0. We are going to use the same approach again and again. So what happens if I tack one more coordinate system to it? So then what you will do is you will again do the exact same thing. New coordinate system as columns, old coordinate systems as rows, and then you will find the projection and get done with it. And this is exactly what is going to happen when we solve the forward kinematics problem for robots. Because this is going to be my first coordinate frame. This is going to be my second coordinate frame. The vertical servo, if you see here, this is going to be my third coordinate frame, and this is going to be my fourth coordinate frame. Unfortunately, these coordinate frames are not very well aligned, but we'll take care of that in just a minute using the exact same approach. Any question? Somebody asking a question in the chat. Oh, okay. Any questions? Now, what I'm going to do is I'm going to repeat, and this is a very important rotation matrix. And why this rotation matrix is super duper important? Because what I can say if is my, and I will write this for the first problem. If I1 is my unit vector in x1 direction, if my J1 is the unit vector in y1 direction, and if K1 is my unit vector in z1 direction, and if I have I0, I have J0, and if I have K0, now what I have is I have a classic linear algebra problem. So what I can say is something like this. If I expand this matrix, this is what I get. I0, J0, K0. And this is where the linear algebra meets robotics. I0, J0, K0. And then I have cosine theta z minus sine theta z, 0, sine theta z, cosine theta z, 0, 0, 0, 1. And I'm going to write this slightly differently, but it means one and the same thing. And I'll explain it in just a second. Give me a minute. So I1, J1, K1. And this is the relationship between the unit vectors in the old coordinate system and the unit vectors in the new coordinate system. Now, what I mean by that is if I were to expand this equation, there is a lot of information just in this simple equation. I0 is equal to cosine theta z I1 minus sine theta z J1 plus 0 plus 0 K1. Then I have J0 is equal to sine theta z I1, then plus cosine theta z j1 plus 0 k1, and k naught is equal to 0 0 plus k1. Now, if you are taking my linear algebra class, if you look at my linear algebra class, in the last class, we talked about something called as the column space. And I want you, just for a second, think about this is the column space of this matrix, this is the column space of the matrix, and this is the column space of the matrix. What that means is, as long as the vector on the left hand side, this is super important, as long as the vector on the left hand side is within the column space of this matrix, everything is good. What does it mean in terms of actual robot? What it means is, as long as the object or the point where we want robot to go into is well within the area that robot arm can reach, we can solve the forward kinematics problem. Second thing that I want you to think about for a second is, if this matrix at any point could become singular, which means is there certain value of theta where that matrix somehow magically becomes 0. And I don't think in this particular case that is possible. But if you have multiple rotations and when they combine together, it is quite possible that one of those terms could become 0, which means basically you cannot solve forward kinematics problem. Now, what I want you to think about is, think about the inverse problem. Inverse problem means, given the left hand side, I want to find out theta. As you can see, these are sine and cosine functions. And when you have sine and cosine functions, it's quite possible that you could have no solution, you could have 0 as a solution, or you could have multiple solutions. And solving the inverse problem is much more involved than solving the forward problem. Forward problem means, given the values of thetas and joint positions, find the location of the end effector. The inverse problem is, given the location of the end effector, find the values of theta and the extension of prismatic joints. So everyone understood this rotation matrix? Now what I'm going to do is, just for my own satisfaction, I'm going to find out the rotation matrices when the rotation is about x and when the rotation is about y. But I know that all of you can easily find these out. So let's do this exercise just once. We won't do it again. This is rotation about z, is a super important rotation. And this is the only rotation matrix that you should remember. Cosine minus sine, sine, cosine. That is the only rotation matrix that you. Yeah.
We do the rotation around z, and if we do this rotation around x1 axis, can we find out the different rotation matrix for that, or will it be related to this?
So what I'm going to do is, I'm going to do the rotation about x, and then I'm going to do the rotation about y. There is a concept of successive rotations. So what I mean by that is, you have x, y, and z axis. So rotation about x and rotation about y doesn't give you the same value if you were to do rotation about y and rotation about x. So basically, the small rotations, they are commutative, which means the sequence of rotation doesn't matter when the rotation they are small, but when the rotations are big, then the final result will be totally different depending upon the order of rotation. And that's why what we do is, if you have rotation issues, we use something called as quaternions, wherein instead of, and I have added some excellent videos on quaternions if you want to see. It's a hypersphere. But in this class, we are gonna look at just the rotation. So what we will do is we'll talk about the sequence of rotations. So let's say the next rotation is about maybe let's say about x, and I will start with the same coordinate frame, same coordinate system. I have x0, y0, I have z0. Now my x1 is gonna get aligned with x0. So this is my x1, and I'm gonna have a positive rotation about x. So this is theta x, and with this positive rotation, I would get rotation in the coordinate frame. So this coordinate frame gets rotated by theta x. Theta x, theta x. And just like the previous problem, I'm gonna draw the perpendiculars. This is one perpendicular and this is another perpendicular. And then what I'm gonna do is I'm going to construct the projection off and projection on. So x1, y1, z1, x0, y0, z0. And now you should quickly tell me projection of x0 on x1. Very good. Projection of x1 on y0, 0. Projection of x1 on z0, 0. Projection of y1. Let me write where y1 is. This is y1 and this is z1. Projection of y1. I want projection of y1 on x0. Tell me what would be the projection of y1 on x0? Really? So projection of y1. So projection of y1 onto x0. I'm going to show you here just a second. This is going to be sine theta x. This is going to be cosine theta x. This is going to be sine theta x. And this is going to be cosine theta x. So tell me, projection of y1 on x0, y1 on x0, it should be sine theta. Oh yeah, y1 on x0 is 0. Projection of y1 on y0, y0, cosine theta x. Projection of y1 on z0, sine theta x. Projection of z1 on x0, projection of z1 on y0, and projection of z1 on z0, cosine theta. Okay, any questions about these rotations? Of course. So let me repeat again. Everyone is clear. Projection of x1 on x0 is 1 because the axis is aligned. X1 has no relationship whatsoever with y0. X1 has no relationship whatsoever with z0. That's why these are zeros. Now what I want you to do is, I want you for a minute to look at y1. And y1, if you look at the projection of y1, there are actually projection of y1. I want you to think about, let's look at y0 first. Projection of y1 onto y0, we agree that this is this. So which is the same direction as y0, that's why it's positive. Projection of y1 onto z0, and I'm going to use a different color pen, is this. So can you see that this is sine? But if you look at the arrow, the way it is pointing, it's in the same direction as z0. That's why it's positive. Now what I'm going to do is, I'm going to look at projection of z1 on y0. So projection of z1 onto y0, and as you can see, that is actually somewhere. I did not draw this perpendicular properly, so that's probably is causing the problem. This is like this. Since it is like this, and this is in this direction. So if you look at this guy, this is in the opposite direction of y0. That's why it has minus sine theta. And now what I want you to do is, I want you to look at this guy. This is actually in the same direction as the g0. So this is cosine theta. So this is c0. So that is how this rotation matrix got constructed. And one thing I want you to remember, whenever you have 1, you are going to have zeros in the columns and rows. So it will always be, if you have 1, the row and the column containing 1 will be 0. Same thing happened here. So if you see here, the rows and columns containing 1, they were zeros. A quick observation. What is the determinant of this rotation matrix? And I'm going to write this down: I0, J0, K0. The determinant of this rotation matrix is actually 1. And in case if you are wondering what is the determinant, the determinant is given as 1. So actually you will have to multiply cosine square theta x minus sine square theta x, and as you can see, the determinant is equal to 1. Now what this means, the other thing which I want to talk about, and I will explain this in the context of linear algebra. So as I said, these are the column spaces of this matrix. So basically this is one vector, this is another vector. So this is the first vector. This is the first vector. This is the second vector. This is the third vector. So if I were to represent this in terms of column spaces, then what I have is 1, 0, 0, I plus 0 cosine theta x sine theta x I1 J1 plus 0 minus sine theta x cosine theta x K1. So these are nothing but the column spaces of the matrix. And as you can see, and this which is super important, that these three column spaces are perpendicular to each other. And the reason they are perpendicular is because otherwise we cannot resolve the vector. If you were to take the dot product or the cross product, you will verify that these column spaces are perpendicular to each other. In other words, this matrix, this rotation matrix, and I'm going to give you I'll denote how that rotation matrix is defined. This is the rotation of 0th frame with respect to first frame, because our initial frame, this is the initial frame, was x0, y0, z0. Our new frame is x1, y1, z1. So this is called as the rotational matrix or rotation matrix from 0 to 1, and this matrix is an orthonormal matrix. So what do I mean by orthonormal matrix? If a matrix is orthonormal, the inverse is equal to transpose. So if you want to transpose this, or if you want to invert this, just find the transpose and you'll be done. What it means is if you want to find the relationship between 0 and 1, you have it. But if you want to find the rotation or relationship between 1 and 0, then what you do is you just transpose this matrix. The last part, and we can stop there, is I'm going to talk about the rotation about, we did X, we'll do rotation about Y. So I'm going to do rotation about Y. Same argument, X0, Y0, Z0. And what I'm going to do is I'm going to rotate about Y, which means my Y1 will be aligned. I'm going to assume positive rotation. And some of you may ask me, and it's a very valid question, that I'm assuming positive rotation. What if in the actual robot, the rotation is negative? What if in the actual robot, the rotation is negative? So nothing changes. Wherever it says cosine, wherever it says theta z positive, just change it to negative theta z, and rotation matrices will take care of themselves. So as far as we are concerned, we always consider positive rotations, and we always consider right hand coordinate system. If in actual problem or in actual robot, those assumptions are incorrect, then what we will do is we'll just change the signs, and that's it. So what I'm going to do is I'm going to do the same thing. I'm going to draw these two, and I will try to be, again, since it's going to be in 3 dimensions, so I'm going to try to be, this is 1, so this is Z1, and this I'm going to call X1, and then I'm going to draw the lines which are sort of perpendicular. Hopefully they look perpendicular. And then, as you know, this guy is going to be cosine theta y. This guy is going to be sine theta y. This guy, this is theta y. This is theta y. This guy is going to be sine theta y. This is going to be cosine theta y. And we do the same exercise. So I have x1, I have y1, I have z1, I have x0, I have Y0, I have Z0. Now, a trick. So first and foremost, I just want to write down uh, the projections we already know. So Y0 is aligned with Y1. Do you agree with me? So which means I will write 1 here. Next thing is wherever you have 1, the rows and columns will be zeros. 0, 0, 0, 0. All right. So in my 3 by 3 matrix, now I just have to find 4 entries. So let's find out projection of x1 on x0. Projection of x1 on x0. Oh, actually I made a mistake here. This has to be, oh, nobody caught it? Sine theta y cosine theta y. So this is going to become cosine theta y. Sometimes I make mistakes to make sure that you are following. Okay. So projection of x1 on z1 is minus sine theta y. Projection of z1 on projection of z1 onto so again I made a mistake here. This needs to look perpendicular. So this should look like this. So projection of z1 onto z0 is z1 onto z0 is sine theta y. Projection of z1 onto projection of z1 onto z0 is cosine theta y. So projection of z1 onto z0 is, so this is not right. This is the projection that we are looking at, cosine theta y, and this is sine theta y. So this is correct. Now again, for completion, I0, J0, J0, and I will have I1, J1, K1. So some of you may ask me, do I need to remember all these matrices? That I would say, if you can remember, that's great. But as far as we are concerned, we are going to use one rule, and that rule is super important. Whenever we have a joint, we will assume our z-axis is going to the joint. Believe it or not, it will make your life super simple. Whenever there is a joint, a rotary joint, we are going to assume the z-axis is going to the joint, which means almost 90% of the times when we solve the problem, the rotation matrix that we are going to use is this rotation matrix. As long as you remember it's cosine theta minus sine theta, then sine theta cosine theta 1. That is the rotation matrix we are going to use 90% of the time when we solve forward kinematic problems. Okay, quick recap. Believe it or not, we finished half of forward kinematics with this, because, well, let me try. What I'm going to do is I'm going to solve a super duper complex forward kinematics problem with the material that we discussed so far. First and foremost, that I have a robot arm, I need to find out something called as the kinematic diagram. So my robot arm, just for the sake of discussion, has 2 joints. So this is one joint, and then I have this second joint. And if you want to see how does this robot arm look in actual practice, it actually, if you think about it, this is this robot arm that I'm looking at, or this robot arm I'm looking at. So you have a revolute joint, and you have the other revolute joint. So there are two revolute joints. So think about that. I moved this robot like this, and now I have two revolute joints which are oriented like this. Step one is always define the base coordinate system. Step two is assign the coordinate system for the second joint. Then, as you can see, if I'm gonna say this is my Z0 and this is my Z1, if I want to find out the rotation of joint 2, if I want to find out the rotation of joint 2, what I would do is I would find the rotation matrix for this guy. I will find the rotation matrix for this guy. And when I want to find out the overall rotation, check this out, 0R2 is equal to 0R1 multiplied by 1R2. So this guy gets cancelled. And finally, I have the rotation 0R2. And that is how we will solve the forward kinematics problem when you're finding orientation. Next time, we'll wrap up homogeneous transformation and start working out problems. I'm going to stop here.